Hi, linear algebra students. This is the second out of 3 videos that aims to prove that if an elementary row operation is performed on an m by n matrix A, then the resulting matrix can be written as a product, E times A, where E is the m by m elementary matrix obtained by performing the same row operation on the identity matrix. So I explained in the last video why this theorem was so important. Why am I so thrilled in proving this? So if you don't quite remember, you can go back and look at the first video. But it's worth reminding that I need this identity to prove this theorem. And it's an identity, remember, that comes from the row column rule or the column row rule actually for matrix multiplication. And it says that the row I of a product, A times B, depends only on the row I of the left matrix of the multiplication. Okay, so that's what makes this proof possible. Okay, so now we're considering the second row operation, the easiest, the scaling operation. So let's suppose that we're scaling a matrix. Okay, remember that when you scale, k has to be not equal to 0. And actually, will I change? Oh no, I will not change k. No problem with that. I don't actually need that k in my scenario. So we consider again, like in the last video, the elementary matrix obtained with that ERO from I. And we want to calculate how the rows of E times A change when you compare them to the rows of A. Okay, so in this, we have here only two cases. Case number one, we consider row J where J is not equal to I. So in other words, we're talking about a row that hasn't been scaled. In this case, then we have that the row J of E times A, and then we use the identity, which is equal to row J of E multiplied with A. And here, the most important part of the argument is that here, we know that when the row operation, so that we're talking about, so Ri going to KRI, doesn't change row J. And that means that the jth row of E is the same as the jth row of the identity matrix because it has been obtained from the identity matrix by a single row operation that didn't change the row J. Okay, so row J of I times A, and then we use this identity again but in the reverse direction. This is the row J of IA, which is the row J of A. Okay, so if you read this from beginning to end, okay, the conclusion is that the jth row of EA is the same as the jth row of A. So what's left is to do the second case if we hit the row that has been scaled. So case number 2, row I. And actually, I'm going to draw the line like this just so that it's a little bit clearer to see. Then we have that the row I of E times A. And we do the same process. The only thing that's going to change is the next step. Row I of E times A. Now, we know that the row operation is row I, K times row I. And it has been performed on the identity matrix. So performed on I. So this means, and I can see I have to change my green. I'll do it right away. So this means that this will be the row I. Oh yes, okay, here I need a little bit more explanation. So it's going to be actually k times the row A, the row J of I. Okay, and then we have A over here. Okay, so now for the explanation. Or actually, let's, yeah, I'll erase this now. So, the row I of the identity is actually quite simple. It's going to be like 0, and then it's going to have a 1, or actually, let's actually write it down. 0, 1, 0, and all the way up to 0. And the 1 is in the ith position. Now, if we scale the row by k, it means that what we have is instead, or actually, let's scale it, right? So, or let's write what is k multiplied with the row I of I. Okay. So first of all, it's k multiplied with the same row. And as you know, whenever you multiply that row by the scalar k, you just multiply every entry by k. So what you're going to get is, instead of 1, you will get k. Right? So this is why it's true. Okay? And as you can see, this is the row I of E. Okay, so hence this step over here. And then as usual, you work your way up to the original thing, right? So it's going to be k times the row I of IA, which is equal k times the row I of A. So again, let's summarize. So, okay, if J is not equal to I, we have that the row J of EA is equal the row J of A. And if J is exactly equal to I, we have that the row J of EA is the K times the row J of A. And from there we can conclude, because we know that EA have the same rows as A, except the ith row, for which it's K times the row A. So we obtained EA from A with the single row operation that scales its ith row by a factor of K. So EA is obtained from A by the elementary row operation And again, this is the end of the proof. for the second row operation. There you are. So in the next video, I'm going to do the third row operation, which is the row replacement. It's a little bit harder to understand, but I will do this type of diagram in order to help you to get it. Here we go. See you in the next video.